Greetings everyone. Welcome back to today's YouTube video. So today we are solving another very interesting problem which is called permutation in string. So this particular question it has been asked in various companies like Microsoft and Google, and the optimized approach of this problem also gives us an understanding of a concept which we can reuse in other complex problems as well. So let's dive into the question. So the question says that given two strings S1 and S2, we have to return true if S2 contains a permutation of S1 or false otherwise. So in other words, we have to return true if one of S1's permutations is a substring of S2. The question is pretty much straightforward. So permutation basically means the rearrangement of the string. So here like we have S1, so the permutation of S1 can be either AB or BA. So we have to spot either AB or BA in S2. So we can clearly see that we have BA here. So the output here is true because we were able to find the permutation of S1 in S2. S2 contains one permutation of S1, which is BA. Now let's also look at example 2. So example 2 is again AB, and we have to spot AB in S2 or AB or BA, both the permutations, any of the permutations. So S2 here we have EIDBOA, OO. So even though B and A can be spotted here individually, but since they are not contiguous, this cannot be termed as a substring. So hence the output here is false. So more or less the problem is pretty fairly easy to understand. So let's look at the approaches we can use to solve the question. So like we were doing right now, we can simply, what we can do is we can figure out all possible permutations of string 1, S1 here, and we can try matching it with S2, like any of the permutations which can be a substring of S2. So looking at all the possible permutations of a small string like AB can be fairly easy, but whenever we move to like let's say a moderate length string, so it can lead us to a very complicated and a very computationally expensive, expensive operation, which can lead us to a time complexity of around big O of n factorial. So just figuring out all the permutations of a string can be as expensive as n factorial. So moving on to another approach, which is slightly better than this one. So what we can do is we can first sort S1. So sorting S1 will give us the string S1 in alphabetical order. What next we can do is generate all possible substrings of S2, which is of length equal to S1. So once we have figured out all possible substrings of S2, which is of length S1, we can sort each of them and match it with S1. So once we have sorted each and every permutation, like substring of S2, so we can get a similar output as of S1 if any of the permutations of S1 exist in S2. And after this, we will simply return whatever the result is, either true or false. If we have found a matching, then we'll return true, otherwise we'll return false. So this particular operation alone, figuring out all the substrings will be n square, and then sorting each substring will be another n log n operation. So total will be n cube log n. So this solution is n cube log n. So now when we have two solutions to the same problem, one is computationally very expensive and the other one is slightly better, which is n cube log n. I think you must be looking for a much efficient approach which you can actually solve in interviews. So what can that be? Let's look into it. So we have S1 ABC and S2 as BBBCA. So what else can we do? We have found all the permutations. We have also looked into every substring possible of S2. Now matching S1 with S2, so we are actually looking at the characters, right? We don't care about the arrangement in which they occur, like it can be CA, it can be BAC, it can be CBA, but always we are looking for is that the frequency of occurring of each and every element should be same. So can we do something around that? So let's look into it. So now let's assume that we look at the frequency maps of both S1 and S2. So for S2, we'll consider only one substring at a time, which was equal to the length of S1. So here, let's say this is S1's frequency map. S1, and the other one is of S2. S2. Here S2 means a substring of S2 that will be matching in a particular instant. So if we decide to create a map where we will be storing each and every element with their corresponding frequency. Let's say for S1, we have A, B, C. And for the rest of the alphabets, like we have 26 alphabets. So for the rest of the alphabets, let's say D, E, F. For every other alphabet, it will be 0. So for A, it will be 1. For B, it will be 1. For C, it will be 1. And for D, it will be 0. So these are the frequencies, corresponding frequencies to the alphabets. And for every other alphabet like E, F, G, H, I, J, for every other alphabet, it will be 0 because it does not exist in S1. So now we know that S1's length is fixed. So we can consider it as a window. Like A, B, C, we can take a window of length 3 and we can keep on shifting the window whenever we are done with one particular substring. So let's say first we will deal with BBB, which is our first window. So for the first window, the frequency map, we'll update it like this. So we will have for A, it will be 0. For B, it is 3. C, it is 0. And D is also 0. So we'll move here. And for every other alphabet, E, F, G, H, everything is 0, similar to S1. So now, how we'll keep up with the matching? So for S1 to be equal to S2 substring, let me update it only to substrings. S2 substring. So just to keep a track of all the matchings possible, for S1 to be equal to S2 substring, we need to have all the 26 alphabets as the same frequency, right? So what we can do is we can maintain a variable here named matching. So matching will be equal to first matching in the first iteration. If we update matching, it will be A is 0, here A is 1, so this is not matching. B is 3 and the B is 1, this is not matching again. C is 0, C is 1, so this is not matching again. So 20, but rest of the 23 alphabets, they are matching correctly. So right now our matching variable will be 23. Now let's slide the window because we need 26 matchings. So now let's slide the window again. So when we slide the window, this time we consider B, B, C. So whenever we are sliding the window, we are removing an element. We are also adding another element, which is on the right. So looking at here, if we look at the next window, we have B, B occurring twice. This is 2. And then C is occurring once. So I will remove this. C is occurring once and the rest of the things remains the same. So now when we match it again, so A corresponds to 1. We have A corresponding to 1. And so this time when we have expanded the window, we are removing one element from the left and we are adding another element from the right. So this time we have in the window B, B, C. So we have updated it accordingly. We have corresponding to B, we have 2 now. And corresponding to C, we have 1 now. So now we are before to update the matchings, we will look at A is 1, A is 0, B is 1, B is 2, C is 1, and C is 1. So this time we found one matching. So this what we'll do is we will update the matching to 24 because only B and A differs. Rest of them has the same frequency. For E, F, G, H, everything still remains 0. So now it still doesn't satisfy what we need. So we'll shift the window once again. So now our window becomes B, C, A. We remove B and then we have A here. We added A to the window. So now updating the count again. So we have A1, B1, and C1. Okay, so this time we achieved what we wanted. A is 1, B is 1, C is 1, and D is 0, E, F, G, H, everything is 0. So now the matching variable updates to 26. This is what we need, and here, then and there, once we have all the matchings approved, so we'll return true. So this is the approach. So the sliding window is an operation takes only constant space, and this length of uh, string S2 is bigger of n. So that's why sliding through S2 will the time complexity will be bigger of n, and space complexity will be only whatever space we are taking to store these frequencies. So if we take two arrays to store S1's frequency and S2 frequency according to the index, like the first 0th index refers to A and first index refers to B, in this way, then the space complexity will be bigger of 26 into 2, which can be written as a constant space. So this is the final solution. So let's look into the code now. Yeah. So we have the function here, which is called check inclusion. So it takes a string S1 and S2. So first is the base case, like if the length of S1 anywhere exceeds length of S2, so we'll return false, because in this way we can never check for inclusion of S1 and S2 because it is not practically possible. Next, we have two frequency arrays. One is both of them are 26 in length, and both will have all the 26 values as 0 initially. Then we will build the frequency count for S1 and for the first window of S2 like we were doing. And we are locating the index which we have to update using this, using the difference of their SI values as a difference. Let's say if S1 ith value is C, so C minus A will give us 2, which is the difference in their SI values. So that particular index, we will be updating the value of that particular index. And similarly for S2 as well, S2 count will also get updated. Then we'll keep the matches variable. We will be updating the matches variable wherever we found a match. So we are having this if condition. If in anywhere we have SI count ith value equal to S2 count ith value, we are increasing the matches. Next, we are using a sliding window approach. We have the left pointer initiated here, and right pointer will be the length of S1 dot length, and which will be less than S2 dot length. And whenever the matches variable becomes 26, we return true. And for sliding the window, we are adding a new character first. So the index is calculated using this. The rth index of S2 minus A, the index of the new character being added. And then once spotted, the frequency of it is getting updated. Then we'll match if the frequencies are same. If they are same, then the matches increases. If we have increased the match which was initially getting matched, so we decrease the matches. So this way we keep the matches in equilibrium. And then similarly for removing the count also, we are calculating the index, then we're decrementing the count. Then we are updating or decrementing the matches variable accordingly. And then for sliding the window from the left pointer as well, we are moving the left pointer. So for the final check, if anywhere the matches variable becomes equal to 26, we return true. So this is basically us returning the value true or false of whether the matches variable is equal to 26. This was the entire solution for the problem permutation and string. I hope you liked the video. Do check out for the more videos that will be coming on the channel. Thank you.